Bonjour, good afternoon, and thank you everyone for coming here to attend this presentation. Hope you enjoyed your lunch. Today I'm going to share some of the work we did on the ExoMars mission, so a very exciting mission. And first off, let me take that remote and test this. Oh, there you go. Very well, so I'll start by saying who I mean by we. I'm here today wearing two hats. So I've been a thermal engineer at MDA for about 10 years in my past life. And MDA, if you don't know them, they're a space company. They've been in the space business for about 60 years now, working a lot on communication antennas. So they've done communication antennas for hundreds of satellites so far. They've done space robotics. They built the Canadarm, the one on the space shuttle, the one on the ISS, and the next generation, which is going to be on the Lunar Gateway in a few years. They've done some extraplanetary missions as well, like ExoMars, that I'll talk about today. And my second hat today will be that of Maya HCT, which is my current employer of the past 5 years. So Maya is a provider of engineering software services and solutions. So they're known for developing TMG in Europe and some structural solutions as well. So they do structural thermal simulations. They do a whole lot more, and they've used people have used their products, for example, on the Mars Curiosity rover, on the James Webb, and many different satellites. And today we do at Maya a lot of different things. We do not only simulation, but CAD, PLM, services, AI, IoT, a bunch of everything. So enough with the sales pitch. Let's talk about ExoMars. So ExoMars, you'll notice throughout the presentation, sometimes I'll talk in the future, sometimes I'll talk in the past. Some of the ExoMars mission has already been done. Some of it will be done in the future, so it's a bit of a combination of both. And ExoMars is a mission to explore Mars, simple enough. So the primary objective is to pave the way for future exploration by exploring, characterizing the atmosphere and the environment on Mars. It's a two-pronged mission. So the first part of the mission which was already done in the past, to send a satellite around Mars, which is called the Trace Gas Orbiter. The objective of the satellite is to monitor the atmosphere from space of Mars and try to characterize what the composition is and the wind and everything on the surface. This satellite also included what we call the EDM, the Entry Descent Module, which is a module whose mission was to go down, separate from the satellite, go down into the atmosphere, and enter as it went through all the different layers of atmosphere on Mars, take measurements, send that back, and then perform a soft landing on Mars. Second part of the mission, which is still to come, is the Rosalind Franklin rover. So it's a rover that's going to land on the surface of Mars. We're hoping in 2028, so don't pay too much attention to the dates here. What we did, both Maya and MDA on this project, is for the satellite we provided a communication antenna. So you can imagine a pretty big antenna to communicate from Mars to the Earth. I'll show you in the next slide. We also provided the navigation cameras for the rover. So one on the end of a robotic arm, another one on the rover body. And the interesting part too is the locomotion system of the rover. And it's very interesting in that it's a 6-wheel system, but it doesn't have 1 or 6 motors. It actually has 18 motors. I'll show you why later. So a pretty complex system. So just to show you what some of that looked like. So the reflector on the satellite for communication was 2.2 meter reflector in the X-band frequencies. And it's a really high gain antenna. It's a Cassegrain type of telescope. And the objective here was to send the system, whatever we measured on Mars, back over 200 million kilometers back to Earth. So it's a very big antenna, very impressive. And what's really impressive about that is the thermal requirements. Since you're so far away from Earth, and as you can imagine, in Earth you have a lot of constraints, you have a very harsh environment, your reflector is going to see a very wide temperature range. And the moment you start having thermoelastic distortions on the reflectors, it distorts. And if you're pointing just slightly off, well, you're missing Earth by a few million kilometers to send your signal back. So that reflector took a lot of iterations between the thermal, structural, and design teams to come up with a design that was very stable over temperature, over the range of the mission. So the images you see here are the actual reflector being on the pivot table at the MDA facilities in Montreal. On the center image, you can see the reflector being integrated on the whole spacecraft with the EDM module that you see on top. Second part of the mission. Oh, there we go, going a bit too fast. Second part of the mission, those navigation cameras on the rovers, those were done by a different division of MDA. And the analysis again done performed by us at Maya. So it included two sets of cameras, two stereo cameras, so one in the visible, one in the infrared spectrum to be able to provide better focusing. And the big challenge here was to try and develop something that used as little power as possible, that managed to stay, cold enough during the day to operate properly, but then survive at night without using any heaters, right? Because we're trying to save up the energy for the rover itself, the rover mission. So you can see again a picture of the rover here with the cameras and wheels and everything integrated on it. I believe that was at S-Tech, but I'm not too sure. And the last one, the interesting part, is the locomotion system, which we call the BEMA, the Bogie Electromechanical Assembly, which is a complex system that had 6 wheels. The 6 wheels themselves are not too complex. And why those 18 rotary actuators and those 18 motors on the wheels? It's because we had to support 3 modes of operation for the rover. One, which is just the simple driving, right? The wheels will spin. Second one is steering. So every wheel on a rover can be steered independently to control the rover. And the second one, which is a bit fancier, is what we call the wheel walking operation. So as you can imagine, you can't send that rover to Mars when everything is deployed, because it's going to be too flexible. It's going to break during launch and re-entry on Mars. So we had to stow the wheels. So we needed to have a third actuator just for the deployment operation. And then we figured if we have that third rotary actuator, what happens if the rover is trying to go up a slope and the surface on Mars is very dusty, right? It's a sand. So if you're trying to spin with those wheels that are about that big, you'll just end up like skittering on the slope. So we introduced the wheel walking mode, which is just essentially the rover walking around, which is a pretty cool video to see. So it shows you here a video of the rover walking up with our thermal model for the wheels themselves in a very simplified rover body. Now, just to give you some perspective on Mars and why this is a challenging project, I'll start by saying typical orbital analysis, thermal analysis are very easy, right? When you're designing something on the Earth, you have to deal with convection, with radiation, with conduction and convection. As soon as you send something to space, you remove one of the 3, which is convection. So no solving Navier-Stokes equation or stuff like that. It's still a pretty complex problem because you're dealing with very extreme temperature environment. But you have 2 heat transfer mechanisms to deal with, which makes it a bit more simple in my mind. Whereas on Mars, the environment is a bit different, right? First of all, it's very cold, minus 100 degrees roughly overnight on the candidate landing sites we were looking at. And you have an atmosphere. Obviously, the atmosphere is roughly 1/100th of the atmosphere that we have here on Earth, which gives us about 1/10 of the convection. And 1/10 doesn't seem too bad for convection, so less than here. But somehow, if you're trying to cool down your heater, your rover when you're too hot, like it's not enough wind to cool you down. And if you're trying to stay warm, well, it's too much wind and it's cooling you down. So it's really the worst of 2 worlds in this case. And some characteristics as well, you get conduction through the air on very small gaps, which is something that's a bit more complex to account for properly in our simulations. The atmosphere on Mars, another point, is mostly CO2. So I'll get back to that later. And you have to deal with dust storms, too, on Mars. So not as bad as what you see in the movies, but still, if you're trying to rove around, there's a small bit of dust that settles on your rover, and you're trying to cool it down, maintain the temperature. It really affects your heat rejection capability. So it's something that you have to deal with in your mission planning. So how did we take all of that and perform our analysis? So what we did is we built our complex rover model here, as you can see, or at least complex for the wheels. And we started integrating everything that has to come into play to properly predict the performance over the whole life of the rover. So we had those transient solar illumination profiles. So the sun travels that is slightly longer on Mars. We had to enter a bunch of different operating scenarios where the transient temperatures of the environment would change. So you have your ground temperature, the air temperature, you have the radiative environment of your rover that changes over time as well. And one thing to note is we know very little about the actual environment on Mars. We've sent a couple of rovers. We had data from the Phoenix mission, which dates back from 2009, which is a while back. And so we had to make somehow conservative but realistic assumptions to get a design that would work without being too conservative and having something that would just not be feasible. So we just plugged all of that into our thermal models. We had to account for wind as well, so we had to enter convection, do some sort of modeling for convection, which is really not typical in space applications, as you can imagine. Account for dust impingement as well, so that dust settling on surface, how does that affect your surfaces? So another thing we had to account for, the internal couplings, conductions, and all the stuff. So if we put all of that together, I'll just give you an overview of one day on Mars on the rover, just to show you what we had to do for the predictions, performance prediction. So let's say you're starting at midnight on Mars. It's pretty cold. Your rover is essentially cocooning. It's in safe hold mode, trying to survive. So temperature is roughly around minus 100, as I said, pretty cold. And then after that, when the sun gets up, while you're sending a multi-billion euro rover on Mars, you don't want to wait until noon, until it's warm enough to start operating. You want to make the most of it. So you start cranking up the heaters as much as possible, and then you heat up everything. You have to make sure you reach your operating states on your rover. And then when you're there, you start operating the rover, and then you have to look at hundreds of different scenarios, right? The rover could be moving in one direction, performing certain operations, taking pictures, taking measurements of the soil. It could be in a crater, it could be a windy day, no wind day, so hundreds, if not thousands of simulations that we had to do to cover the whole performance using our digital twin for the wheels here. And when you've completed your whole day, then you go back into your cocooning mode. You're trying to save power as much as possible. So you just store everything, turn off the power, and try to crank up the heaters again to survive for another night and live another day. So once you predict the performance, I think it's cut off a bit. So once you predict the performance of your rover, it's all nice and well, but we actually know very little about Mars, as I said, so we actually need to test everything in an environment that's representative of Mars. And that also is something that's very complicated to do, right? Because there's not a single company on Earth that builds thermal chambers to reproduce the environment on Mars. It's really a unique environment. We go very rarely on Mars. So we had to think about it for a while and figure out how to use our equipment to reproduce that environment. So what we ended up doing is we took one of our TVAC, or thermal vacuum chambers, and then we completely removed all of the cryogenic pumps, which allow you to reach hard vacuum, which is more vacuum that we're trying to reach. On Mars, typically the pressure you want to have to reproduce the environment would be between 0.1 and 10 atm on the graph here. So we removed all of those hard pumps and replaced them by mechanical pumps. So a set of mechanical pumps that would allow us to reach a partial vacuum, just enough to be in the zone we want to be to represent Mars. And the second challenge here is that if you have a partial atmosphere and you're trying to do that on Earth, well, your partial atmosphere will be air which has humidity. So the moment you go down below 0 degrees, you'll start condensing and you'll start to have ice forming on your rover wheels, which is not something that you want in a TVAC. So typically TVACs come with nitrogen purges to do the purging and keep the environment safe, but that was not good enough. We wanted a real CO2, so we had to pull out all of the nitrogen purge system, replace that by CO2 lines. And by adding a couple of very precision valves, we were able to just inject enough CO2. At the same time, we are pulling vacuum on the other side to maintain that environment in the zone we wanted, which is, as I said, between 0.1 and 10 atm with the right atmosphere. So with that being done, we had a couple of additional challenges to deal with. Don't remember if I mentioned that when I talked about Mars, but Mars has something peculiar, which is snowfalls, because at the combination of temperature and pressure on Mars, the CO2 can actually solidify, and it can become snow. That's something that we've observed with previous rovers on Mars. So in preparing for our testing and validation of our digital twin, we had to make a test plan that made sure we stayed below that curve of solid CO2, which was a challenge in itself. And then we had to think about, well, what happens if there's a power failure? You know, right? We're in Quebec, it's winter, there's snowstorms. What happens if you lose power? Pressure goes up instantly, and you end up with snow in your TVAC, which is not something that you want to have ever. So we had to install a lot of fail-safes and generators and everything to make sure it could operate nonstop for a few months. And last thing, which was also novel, I would say for me, is TVACs, they operate in vacuum, right? So if you have a unit inside the TVAC, which is at minus 100 degrees, the walls of the TVAC, the shroud of the TVAC, it's all low emissivity. So your walls, which are like several tons of aluminum, they're going to remain at roughly room temperature, even though the inside is very cold. But we quickly realized when we did the dry runs for the test that with just a little bit convection, the walls of the TVAC actually became pretty cold pretty quickly. So we started to have condensation on walls and then frost on the outside, which is, again, not something we want to have to deal with. So for the first time, and I've never seen that before, we had to open the TVAC and start adding insulation on the inside of the TVAC, so foam, insulating foam for the TVAC. So interesting problem to discover. So with all of that being done, we were able to successfully deliver all of the contributions to the ExoMars mission. So just a quick status update on the mission as of today. The trace gas orbiter has been sent since 2016 around Mars, and it's been successfully gathering data for 6 years until we lost communication in 2022. The EDM, so that entry descent module, was a mitigated success, which is what we call something that's supposed to soft land but crashes on the surface. It did have some success because it managed to gather data as it was going down on the atmosphere and send that data back to the satellite and then back to Earth. So we were still able to learn a lot about the Mars atmosphere with the EDM. The rover, it gets a bit complicated because one of the main partners of the mission for the rover was Roscosmos, the Russian space agency, and because of the political turmoil, they decided to pull out from the project at some point, which forced ESA to turn around and try to find their nuclear power cells somewhere else, which is not something that people just have lying on the shelf. So they've made an agreement with NASA. I believe Thales is leading the mission now to try and get back on track and send it to Mars by 2028. So last quick word, maybe why talk about Mars today? Well, we know in the US there's been a lot of focus over the last few years for moon exploration with the Artemis mission. But we can see and we can feel that Mars is going to be back to the center of interest within the next few years, I believe, with what's going on in the US and they're driving space exploration. So that's it. Thank you for your time. If you have any questions, if you're a space enthusiast, if you're working on interesting stuff, come see us, booth B12. Happy to have a conversation.